We'll get started. So, a quick announcement: the quiz one will be uploaded very soon, maybe today or tomorrow, and I'll let you know. It's based on lecture one and two, so all the preliminary material, which is vector spaces. Most of the questions are going to be true, false, multiple choice questions. So, as long as you understand the material about vector spaces and linear operators and things like that very well, you should be able to solve that. All of that. You will get 1 hour. Do not start the quiz unless you are in a frame of mind to actually complete the quiz, because you only have one chance to answer all the questions. Use of AI is prohibited for the quiz, but for assignments, assignment one will also be uploaded very soon, and there will be one question where you can use AI to solve the problem. So the president of the university wants all of us to be AI literate, so it's my duty to give you guys some assignment problems where you can use AI to solve the problem. Okay. So today the topic for discussion is the following. So in the previous lecture, we were talking about x dot t equals to f of t xt. This was our problem, and we were concerned about two questions. Is there a solution? Oh, x t naught equals to x naught. Is there a solution phi? And the question two is it unique? Okay, so we are going to talk about two theorems. We are not going to prove that in the class because that requires us to have a very good understanding of functional analysis and the notion of compact sets in infinite dimensional spaces, and Banach contraction mapping theorem, things that we have not talked about in this class. So we won't be able to go into the proofs of the results that I'm going to talk about right now, but know that, oh, you can use AI to figure out what the proofs of these statements are, because I use Gemini quite a lot, and Gemini was able to give me the proof. So you can also trust Gemini, and hopefully it'll be the same proof that it showed me with high probability. Okay. So the first statement is, the first theorem essentially answers the question number one. So I'm going to take you back to 1890s, and the theorem is Cauchy-Peano's existence theorem. I'm going to write 1890 plus epsilon because I don't know. It was proved around 1890s. I don't remember the exact year now. And it was proved by Peano. And the statement is, if f is a function which is a continuous function from domain D to Rn, and D is a subset of R cross Rn, then for every T naught x naught in D, there exists C greater than 0 such that phi T exists for all T The second theorem, which is about the uniqueness, which answers the second question, is Picard Lindelof theorem. if for every compact set K subset of D, F is Lipschitz in X, that is T comma X minus F T comma Y is less than equal to L X minus Y. For all Tx, Ty in K, then there exists a unique there exists C greater than 0 and a unique P T I don't know when Picard-Lindelof theorem was proved. Maybe 1930s, 1920, 1930. I don't know. Okay, so what's the setting here? So somebody did a very complex analysis and figured out the differential equation governing a specific system that we are interested in. It could be a rocket going into the space, it could be a underwater vehicle, it could be a humanoid robotic, it could be anything, right? So there is a dynamical system, and the behavior is governed by this ordinary differential equation. We want to know two important things. The first thing is there a solution to this differential equation, ordinary differential equation? And the second is it unique, right? Because we saw some examples of ordinary differential equations in the previous class. We saw one example where there was no solution. We saw another example where there were two solutions to the differential equation. So ideally, if we are trying to solve a problem, we want to have a unique solution because we don't want to deal with multiplicity of solutions. So the two questions that naturally arose back in 1800s was, is there a solution to this problem? Then Peano came in 1890s and said, look, if f is continuous over the domain and domain to Rn, so domain D is where the state and the time axis lies. State and so this is the time axis, this is the state. Naturally, this D contains T naught and X naught because we want to make sure that the domain contains the initial condition, the way we are initializing the problem. So if I have a rocket, I want to make sure that the domain is on the Earth and the tube that goes along all the way to the space around the spacecraft. So that's my D. So for every T naught and X naught in D, there exists a constant C greater than 0. um, such that the solution to this differential equation exists for all t in this particular time interval, t naught to t naught plus c. Okay, t naught plus c is open, t naught is included. So because we know that x of t naught equals to x naught, so this is included. But this endpoint is not included. So it's open interval t naught plus c, and it's closed at the t naught side. So keep that in mind. This is not a typo. This is exactly what it is. It's an open interval on this side. Okay. So that solved the existence, but the uniqueness still remained a mystery for a few years until Picard-Lindelof theorem came out, which said that we pick a compact set. What's a compact set in R cross Rn? It's a closed and bounded set. So if we pick any compact set within the domain, f has to be Lipschitz in x. Okay, so it doesn't have to be Lipschitz in t, it has to be Lipschitz in x. What does that mean? F of tx minus f of ty. So remember, I'm not changing the t, I'm only changing x and y here. I'm taking the norm. This could be any norm. If it is Lipschitz, so L multiplied by norm of x minus y. This should hold true for all tx and ty pair in K. Then there is a unique solution to this ordinary differential equation in the interval t naught to t naught plus c. T naught plus c is open, t naught is closed. Okay. This theorem, for those of you who might be aware of functional analysis and who might have taken those courses, this theorem is proven using Arzela-Ascoli theorem, which allows you to prove the existence. This one is proved using Banach contraction mapping theorem, and typically the C value is roughly 1 over L. Okay. So that explains the behavior. If we have a Lipschitz function in X, it could be discontinuous in T. That doesn't matter because we don't require any continuity. Well, we do require continuity with respect to T, but we don't require Lipschitz continuity with respect to T. But we do need Lipschitz continuity with respect to X to establish uniqueness. Okay. Any questions so far? Now, sometimes in problems of this type, we have parameters, which means that we have x dot of t equals to f of t xt lambda. So lambda is a parameter. So where do we have parameters? I drive my vehicle. Sometimes only I'm in the vehicle. Then I go to the grocery store. I put the grocery on the vehicle. So the mass of the vehicle has increased. Then my wife comes in, my kids come in, the mass has increased even more. Then they get off to some place and they take the groceries away. For instance, if we are going to our house, then suddenly the mass has decreased again. So I have lambda, which is the mass of the vehicle, and it's changing depending on one trip, depending from one trip to another. In the case of rocket, typically mass of the system would be the state itself because the mass is changing every second. So actually m would be, the mass of the rocket would be part of this description of x dot. It won't be lambda. But lambda could be the structure of the rocket. So I don't know if you've seen, but whenever rocket goes up in the sky, then it starts shedding some amount of machinery as it goes up. And so lambda could be, what all things is still around and what all things have been shed off by the rocket. For a vehicle, for a battery pack, let's say you have a battery pack, X is the state of the battery pack, how good the battery is doing, the current and voltage characteristics of the battery. Lambda could be the internal situation in the battery. So for instance, you have 10-year-old battery, then certainly the cathode and anode might have gone through some degradation. The electrolyte solution within the battery might have gone through some degradation. So lambda would be sort of the degradation parameter of the battery. So anything that ages, in the vehicle, the tire pressure also changes, right? So today it's very cold, so the tire pressure is low. Tomorrow it will be hot, the tire pressure will become hot. Day after tomorrow, there is a winter storm coming, so the tire pressure will be extremely low. And then the check check tire pressure light will turn on in your vehicles, and that's another lambda, that's another variable that uh, changes the dynamics of your system. Anybody knows what happens if the tire pressure is low on your vehicle? How does it change the dynamics of the vehicle? The friction increases, right? So the car becomes more sluggish. Um, and if you put a lot of air in your tire, if you have filled it to the maximum extent, then your friction reduces a lot, and then it becomes dangerous to drive on icy conditions. So over the weekend, make sure that your tire pressure is low, okay, not high, because it'll be a lot of ice on the road if you're driving. Okay, so sometimes we have situations where we have parameters, and then we want to ask the same question, and essentially the theorem is, I'm not going to write the complete theorem, but essentially you want Tx lambda minus f of Ty lambda is less than equal to Lipschitz coefficient minus x times y for all T lambda in some interval J naught cross G naught. J naught is an interval of R, G naught is an interval of Rm. So the parameter lambda lies in Rm. You have m dimensional parameters. So I have 4 tires in my vehicle, and I have the mass of the vehicle, so I have 5 dimensional parameter set that describes my vehicle today. Okay. By the way, the friction coefficient of the road is also a parameter. Okay, so if it is raining, the friction coefficient of the road changes. So you know, the more number of parameters you add, the more complicated your system would become. But I just want to give you an idea of what these parameters would mean in a real system. So if this holds, if this condition holds, and I want to make sure so this is to be true for all x, y in Rn. So for some reason, the book says that this has to be Rn. I'm pretty sure you can replace Rn with some domain D, but the book is saying xy has to be in Rn, so I'm going to write xy is in Rn. Then in this case, there exists a unique solution, phi t lambda. Okay, so we have a lot of situations where there is a parameter and the parameter changes, and then we want to be able to figure out what the solution to the system is going to look like. You know, one more good example of this is, you know, those sprayers which you use in your garden, like the garden hose, and lambda would be the pressure of the water. If the pressure of the water is low, it's just going to push the water out in a specific direction. As soon as the pressure changes, it goes above a critical threshold, it starts rotating, and then you see this rotating behavior of those garden hoses which have this rotating water spraying system. Okay, so lambda would be the parameter there, which is the pressure of the water. And depending on the situation, if the pressure is below a certain threshold, it has a certain behavior. If the pressure is above a threshold, it has some other behavior, which is sort of a cyclic behavior, a periodic behavior. And that is studied under the umbrella of bifurcation theory. We are not going to talk about that theory in this class. It's part of nonlinear systems class. But I just wanted to give you that example as well, where there is a parameter and the system behavior changes quite significantly as you move the parameters, as you change the parameters in a specific way. Okay, so bifurcation is a very important phenomena in many systems, but but we are not going to be talking about in this class. Especially in linear systems, there are no bifurcation, so it's not that important, but in nonlinear systems, bifurcation is very important. Any questions so far? Okay, so if we were in 1850s and we were given a differential equation of that type, we wouldn't know if a solution exists to those differential equation. But now, after 1920s, we know not only the fact that the solution exists, but it's also unique under certain circumstances. And in fact, the parameterized solutions also exist and unique under certain assumptions. Okay. Now the second question becomes, how do we compute the solution? So existence is given, uniqueness is now given. The question now becomes the computational tool. So what is the tool that allows us to compute what the solution to this differential equation is going to look like? So let's study that. So that's studied under the umbrella of Picard iteration or method of successive approximation. So we'll talk about that next. Any questions on this material? Okay. Okay, method of successive approximation, which is also called Picard iteration. You know, the thing is, I've heard of this term method of successive approximation in multiple fields. Uh, so I don't know what the reason for calling it method of successive approximation is, but Picard iteration is specifically used for this particular topic. So method of successive approximation is a computational approach to solving this differential equation. It's one way to solve this differential equation. How many of you have heard of this ODE solvers in MATLAB or Python? Some of you have used it, right? So those solvers, the ODE solvers that you use, that you see in MATLAB and Python, they use completely different methods. They don't use this method of successive approximation. But this is actually one way to solve it. And as you will see why it's not useful for actual computation, but it's actually very useful for a conceptual way of understanding how to compute the solution to these differential equations. So what is this method? I'm going to define my phi of t equals to x naught for all t in t naught plus c. Oh, phi 0, sorry, phi 0 of t. I'm going to define phi 1 of t as x naught plus integral t0 to t oh no perfect. Then I'm going to define phi2 of t and so on. Okay, so what did we do? We started with x naught. We started with a function phi 0, which is uniformly equal to x naught for the entire time interval t naught to t naught plus c. Then I substituted this phi naught here in this expression for f, and then I did this whole integral in order to get the value of phi 1. And then I put this phi 1, I have the first estimate for this differential equation. I substitute it here, then I get phi 2, and I keep going on and on all the way up to infinity. The reason why we don't use it in MATLAB or Python is because we don't have a method to compute this infinite series in MATLAB or Python, right? So if each of these iteration takes 1 millisecond and you have to do infinite number of iterations, you will need infinite amount of time to be able to compute the solution to this differential equation. So as a result of which, MATLAB and Python doesn't use this method of successive approximation or Picard iteration to solve differential equations of this type. Nonetheless, we'll see maybe today or maybe in the next class that this is actually a very good conceptual tool if you wanted to solve linear differential equation, because it will lead us to what is known as matrix exponential and allow us to compute the solution using matrix exponential. But more on that a little later. The benefit of deriving it this way, so remember the assumptions of Picard-Lindelof theorem. So under assumptions of the theorem is under assumptions of Picard-Lindelof theorem, which means that f is Lipschitz in X, phi m minus phi infinity goes to 0 as m goes to infinity. So this, remember, this is a continuous function. So because it's a solution to a differential equation, it's a continuous function. I'm endowing this continuous function with infinity norm. And so phi m essentially is in C R to D, or I should not write the whole R, but T naught plus C to D. So it's a continuous function from T naught to T naught plus C to D. And if you endow this with the infinity norm, this particular norm goes to 0 as m goes to infinity. So if you keep doing this again and again, if you keep running this operation again and again, eventually you will converge to the solution to the differential equation. Any questions so far? The book doesn't have the proofs of all the statements that we are making, once again, because the proofs require quite a bit of mathematical machinery. But the book has the reference where all the proofs are provided. So if you're interested, you can certainly look up the proofs in those references. Or alternatively, you can use Gemini or whatever is your favorite AI tool to see what the proofs of these statements look like. These statements are generally extremely old in the sense that many of this stuff uh, were proven back in 1920s and 1930s. So I'm pretty sure the AI tools will not give you the wrong answer, but be wary of using those tools in case they are hallucinating. Let's try to apply these ideas. So let's look at the first example. Suppose my problem is x dot t equals to axt plus gt. This is the problem, and I want to show. Oh, there was one point I did not mention, but I should mention. Remember, we mentioned in the context of Picard-Lindelof theorem that you can pick any norm. One thing I want to mention here, that you can have functions that are Lipschitz with respect to some norm, but not Lipschitz with respect to other norms. Okay, so you have the freedom to pick whatever norm you want, but keep in mind that just because you picked a specific norm, it's not Lipschitz with respect to a specific norm that you picked, doesn't mean that it will not be Lipschitz with respect to some other norm. It could be Lipschitz with respect to some other norm. Just something to keep in mind. Anyways, going back to this particular example, suppose we want to prove that the solution to this exists and is unique. How would you prove that a solution exists to this particular problem? What are the conditions under which a solution would exist to this specific problem? Yeah.
I guess A would have to be negative semi-definite, and I think there's some restriction on G, but I'm not sure what that is.
Okay, A negative semi-definite, some restriction on G. Okay. Remember, we are not looking for solutions all the way to time t equals to infinity. We're just looking for solutions. So x of t naught equals to x naught, and we want to be able to construct the solution in the vicinity of that t naught x naught pair. And I think negative semi-definite is also somewhat of a strong condition. We don't need that condition. But remember, okay, let's go back to our original assumption. What was the assumption for existence? We wanted this. This is my f of txt. What was the assumption on f under which a solution exists? It has to be continuous. That's it. So under what condition is this particular mapping continuous? We want G to be continuous. Is A times X, is that a continuous function of X? That's a continuous function of X. So in short, if G is continuous, then a solution to this differential equation exists, but it's not unique. When is it unique? When is it unique? Remember that f of tx minus f of ty, I mean, f has to be Lipschitz with respect to x. Is f Lipschitz with respect to x? So let's look into it. So what is f of tx minus f of ty? This is ax plus gt minus ay minus gt. A x minus y. Is this a Lipschitz function? Is this a Lipschitz function of, so is f a Lipschitz function of x? So what is norm of f tx minus f ty? this is less than equal to the operator norm of A, x minus y. So if A is a finite matrix, I mean, of course, all the A matrices that we are considering in this class will have finite entries. The norm is going to be finite, so this function is Lipschitz, as a result of which this will always have a solution, a unique solution. So if G is continuous, it will have a solution, and in fact, it will have a unique solution because F by definition is a Lipschitz function of X, no matter what norm you pick, because this will be bounded no matter what norm you have on Xn, on the space of Rn. Any questions so far? Perfect. Let's consider the second example. We have a simple linear time varying system. If we apply the method of successive approximation, what exactly is the evolution of the dynamical system? So let's do that. No questions here. I'll erase this. So I take the time derivative of x, it's equal to time varying matrix A multiplied by x of t. I'm going to define phi 0 of t equals to x0. What is phi 1 of t? It is x0 plus integral t0 to t a s x0 ds. Let me use S1. Am I doing it correctly? Did I make any mistake? No? Identity plus integral t naught to t a s1 ds1 times x naught. Looks correct? Awesome. So what I get is phi 1 is actually a matrix. This is a complicated matrix, okay? You have to evaluate some matrix valued integral and all that stuff. That's fine. But this is matrix multiplied by x naught. Okay, what about phi 2 of t? X naught plus integral t0 to t a of s2 phi 1 of s2 ds2. Okay, so phi 1 of s2 is given by this expression. So what should I do? I'm going to replace this by this. Does that sound reasonable? That's phi 1 of t is given by this, so I'm going to replace. So I have s2 here, which means that this t will become s2. Okay, so this, what I get is x naught plus integral t naught to t a s2 identity plus integral T naught to S2 AS1 DS1 X naught DS2. Does this look correct? Looks correct. Okay, so I can again rearrange the terms. I have identity plus integral of T naught to T AS2 DS2 plus integral T naught to T integral T naught to S2 AS1 DS1 DS2 times X naught. Do you guys see a pattern? Is there a pattern here in this example? What is the pattern that we see? So if we keep doing this thing again and again, what we will get is a matrix which requires a lot of computation. We get a matrix times X naught. So this is generally P T T naught X naught. This is the solution to that differential equation. And what is the property of this matrix? The property of this matrix is d phi t t naught over dt is equal to at phi t t naught. It has this sort of recursive structure. You take the time derivative, it's equal to the matrix at that time multiplied by the matrix itself. Remember that this phi t t naught is in R n cross n. Okay, so this is the cool result that you get through the method of successive approximation or through the method of Picard iteration. If we didn't have Picard iteration, we wouldn't be able to get such a nice closed form solution, which is a matrix multiplied by X naught. And how do we get the matrix? Well, the matrix satisfies this condition. So as long as we can do the integration, we will be able to compute the matrix. What are the methods that people typically use for solving this kind of differential equation? Well, in MATLAB and in your favorite solvers, you can use ODE45 or many other solvers that are available to be able to solve problems of this type. Okay, so this is an n square differential equation. This is an n square dimensional differential equation that you need to solve. Okay, so you can solve it this way, or alternatively, this x naught remains fixed. You just have to compute this matrix and you do it this way. Okay, so that goes for a time varying matrix where a is a function of t. So because a is a function of t, all of these integrals are very complicated. Okay, these integrals are very complicated. I'm not able to integrate this thing unless I know what the matrix A looks like. However, if A is time invariant, which means A doesn't depend on T, then actually this whole thing looks somewhat manageable, right? So this is time invariant, so I can pull the matrix A out, and then it just becomes integral of T naught to T of ds1. Sounds easy. If I can compute this, if A is time invariant, I can pull this A out, then this is the double integral actually. So let's see, I know this one is easy to solve. Well, let me write that down. So what is, so AT is equal to A for all T. So A is not varying with time. Then what is integral of T naught to T A S1 ds1? This is just A of T minus T naught. So this one is A times T minus T naught. What about integral T naught to T, integral 0 to S1 ds1 AS1 ds1 ds2? This is A. Can someone do this integration and tell me what this value turns out to be? So I'm pulling the A matrix out because A doesn't depend on S1 anymore. So all I have to do is integral of 0 to S1 ds1, integral T naught to T ds2. Oh, sorry, this is S2. That's what I thought. This is S2.
T squared minus T naught squared plus
What did you say? T?
T squared minus T naught squared plus
No.
1 over 2.
Sorry? 1 over 2 of what?
T squared minus 1 over 2 T 0 squared.
No. There is 1 over 2 for sure, but it's not T square minus T naught square. It's something else.
T square T minus T naught square.
Perfect. T minus T naught square over 2 factorial. Do we see a pattern here? What's the pattern? At every point of time, I do this integral. I get A multiplied by T minus T naught raised to M over M factorial. That's what we are going to get. Awesome. Any questions so far? I hope I'm not going too fast, but please look at that expression, convince yourself, ask any questions. Okay, so this is my phi2. So let me write down. So phi1 of t is I plus a t minus t naught over 1 factorial x naught. Phi 2 of t, let me write it below, I plus a t minus t naught over 1 factorial plus a t minus t naught square. You know, I think I have made a mistake. There should be an AS2 here. This AS2 will also get multiplied to this integral. Can you please go back and check? I think this is missing. A of S2, which should get multiplied outside of the inner integral, but it should be under the first integral. Do you all see this term, A times A of S2 here? So I have to have A of S2 here as well. And then I'll get A square. Okay, please make this change. A of S2 has to be there in this integral. Okay. Do you see a pattern now? So we saw a pattern here. We saw a pattern here. This is what phi 2 of t looks like. So what is phi of t? This chalk is not good. Phi t, remember phi t is the limit of this process. Phi 0 of t, phi 1 of t, phi 2 of t, and so on. So what is phi t? It is identity plus summation t equals 1 to, not t, m equals 1 to infinity a raised to m t minus t naught raised to m over m factorial x naught. This is my phi of t naught. Does this look familiar? This is example 2. And this is example 3. Okay, so does this give you a crazy flashback of your calculus class? What does this look like? Exponential function, right? So what is exponential? 1 plus x over 1 plus x square over 2 factorial plus x cube over 3 factorial, which is exactly what this looks like. So actually we call this matrix exponential. Exponential of a t minus t naught. So you can think of it as 0th order, a raised to 0, t minus t naught raised to 0 over 0 factorial. That's this number. And the rest of the terms are here. This is a matrix exponential. So I know so far you have heard about exponentials for real numbers. When you took signals and systems, or when you took complex numbers, or when you took feedback control systems, you took complex exponentials, so exponentials of a complex number. So how did we do exponential of a complex number? Well, we took the real part, and then we took the complex part out, and then the complex part disintegrated into sine omega t plus cos omega t plus j sine omega t. So that was complex exponential. Now we are introducing matrix exponential. So this is now a matrix. This is an n cross n matrix. I'm multiplying it by a scalar t minus t naught. So this is a matrix. Now I'm taking the matrix exponential. And this matrix exponential is in a short form. We write it as phi of t comma t naught. And the property which phi inherits that property from here is, if you do the first derivative of phi with respect to t, you get a phi t t naught. Okay, this is the case when a doesn't depend on time. Okay, so that's why method of successive approximation is kind of a powerful tool, because we can solve some of these problems by hand, even though we cannot use it on a computer. So it's not good for computer, but it's good for coming up with ways to solve problems of this type. Any questions so far? Now you can go back home and boast about the fact that you know matrix exponential. You can be excited, call up your mom and say, hey mom, I learned about matrix exponential. She'll be so happy and proud of you. Okay. Okay. Okay, so we started with this nonlinear dynamical system. Then we said, okay, under certain condition, there exists a solution. Under certain more condition, there exists a unique solution. Then we figured out a method of successive approximations to solve problems of that type. Then we said, oh, well, you know, it's fine to do it in theory. Let's try to see some examples or applications of that theory. So we applied it on this linear time varying system and linear time invariant system, and we figured out, okay, the solution kind of looks pretty cool. The solution of this sort of problem is some matrix exponential multiplied by x naught, so initial condition. In other words, the solution is a matrix multiplied by the initial condition, so it's actually a linear operator. So the solution is actually a linear operator over the initial condition, which is a pretty cool thing, matrix multiplied by the initial condition. The matrix is definitely time varying, and it's given by this particular expression. Now we have a nonlinear system, very complicated nonlinear system. I'm sending a rocket to space. It has to go and push the satellite into an orbit. And it's a highly nonlinear system. It's kind of an inverted pendulum, but it's a powered inverted pendulum. So if we do not power the rocket is going to come down and crash into the ocean, but we need to power it so that it always remains upright, and it kind of goes up and injects the satellite into the orbit that it was designed to inject into. So now we have a nonlinear system. I want to still be able to control that nonlinear system. We have learned all this linear systems theory. How do we control a nonlinear systems using linear systems theory? Okay, that's a difficult problem. So let's try to think about it. So I have this earth. I have this rocket. It has to have some fins. So I have this rocket, I'm going to send it to the space. So the trajectory of this rocket is going to look something like this. That's the trajectory of the rocket. Okay? It's a highly nonlinear system. So the dynamical equation is x dot t equals to ft xt. I know I'm not putting ut here right now. So let's just do the simple case. So somehow it's an unpowered rocket. So I don't know who's propelling it, but it's an unpowered rocket going into the space. It's magic. Okay. So we are in the Harry Potter world for the time being. So this rocket is going. It's following this dynamical equation. There are physicists sitting in NASA who have derived and given this highly complex nonlinear system to us, and they have asked us to design the control system for this, or at least try to understand what happens in this system. So what we are going to do is, instead of trying to approximate this nonlinear system over the entire space, what I'm going to do is I'm going to create a small tube around the trajectory, and I'm going to approximate this nonlinear system in this tube. Okay. So my original trajectory is this. This is my original trajectory. Around the original trajectory, I have created a small tube. And now I want to approximate the system around this, within this vicinity of this trajectory. So how do we do that? What is going to come to our rescue is Taylor series. So as long as f is differentiable with respect to x, so I want my function f to be differentiable with respect to x with continuous first derivative. I'm going to denote it by f is in C1 d2 Rn. So it's differentiable with respect to x, and the first derivative is continuous, and the gradient of f is so this is gradient of f. Okay, what is gradient of f? I know you have not taken the optimization class, so I have to introduce the derivative of a multivariate function. F of x equals to that's how you define the derivative of the function f. So in fact, this should be Rn cross n, because the gradient of f is a n cross n dimensional matrix. So I have a system, autonomous, not an autonomous, but a system which is driven by just a function x dot equals to f of tx. I assume that f is differentiable and it has continuous first derivative. And I'm looking at the nominal trajectory. This is phi of t. And I'm looking at like vicinity of phi of t. And I want to figure out what is the trajectory going to look like around this trajectory phi of t. Why should we be interested in this? So, the reason why we are interested in trajectory around the feasible trajectory, the trajectories which are sort of perturbations of the original trajectory, is because when you actually launch the rocket, you suddenly realize that there is a crosswind of 10 miles per hour, or the rockets were designed to provide the thrust of 3000 Newton meters per second, but now in fact it is giving a thrust of 2999 Newton meters per second. So there are these small issues, small changes to the actuators, to the sensors, and in the environment because of the airflow and because of the temperature gradient and because of a lot of different things that are happening in the environment. So your trajectories will not be the exact trajectory that you had calculated. It will have some perturbations around that trajectory, and we want to figure out what is that perturbation going to look like. Okay, so let's say my x of t, the true trajectory is my phi of t plus delta x of t. So this delta is not a multiplier to x of t. Delta x is a variable in itself. Are you familiar with this delta x kind of variable? I'm sure you've seen it in calculus classes. So it's not multiplication of delta with x. It's a variable in itself. So I'm looking at this. So what is my f of t xt? This is f of t phi t plus delta xt. I'm going to apply Taylor series, so I get f of t phi t plus gradient f with respect to x, gradient with respect to x of f t phi t multiplies by delta xt plus higher order terms. So there will be delta x square term, delta x cube term, delta x raised to 4 term, and so on and so forth. Just the usual Taylor series stuff. And so what do we get? We get x dot t minus phi dot t is delta x dot t, which is given by gradient x f t phi t plus higher order term. And I'm going to call this matrix as A of t. Okay, so we had the original trajectory. We got perturbed because of the wind, because of the actuators not being accurate, not providing the accurate thrust, because the air density has changed, because of this, because of that, like 500 reasons why things can have different parameters than what we had assumed. Or we could have a situation where our model itself is an approximation of reality. And so we have this perturbation term. We did the derivation and we realized that actually the perturbation derivative with respect to time is going to be a matrix getting multiplied by the perturbation itself plus some higher order terms. If the perturbation is small, the higher order terms are going to be very small, right? Because this contains all the delta x squared, delta x cubed, delta x raised to 4 term. So this term is going to be small. So actually this is going to be the dominant term. So I can write this statement as z dot t equals to at zt. I can analyze this particular expression. I'll get some value of zt, assuming that value of zt is very small. So these are small perturbations around the nominal trajectory. I will be within the linear system setting. I can solve this problem using the linear systems theory. As long as this is small, I'm guaranteed that the higher order terms are going to be small as well. Okay. So to understand the behavior of the rocket around the nominal trajectory, you can go through that linearization procedure, and what you get is a linear system, and you can study this linear system. You can show that the state of this linear system is going to be small. So if z0 or zt naught is small, if zt naught is small, then zt is small. This is something we need to show. But if this is small, then the higher order terms will also be small, and therefore you will send the rocket and it will be around the nominal trajectory. It won't be exactly at the nominal trajectory, but it will be in that vicinity. So your nominal trajectory was the satellite was supposed to revolve around Earth at 2000 kilometers above the Earth's surface, but instead it's revolving around 2001 kilometers above the Earth's surface. Do we care about that 1 kilometer? Not really. If it makes us $1 billion, I don't care about this error of 1 kilometers when it's 2000 kilometers away from the Earth's surface. Okay? That's the business model of Tesla. Not Tesla, sorry, SpaceX. Okay. So this term so z dot t equals to at zt, where at is gradient of f with respect to x evaluated at the nominal trajectory. This is known as linearized equation about the nominal trajectory. Okay, we can have the same problem when you have a control signal as well in the state transition function. So we move from Harry Potter world to real world. So in Harry Potter world, there is no control action. Everything happens by magic. But now we have a control action. So x dot of t is f of t, phi of t, psi of t. So what is psi of t? This is my control signal. One important note I want to make here, this is an open loop control signal. It's not a function of state, it's not a function of x of t. I should say phi dot. So this is the solution to the differential equation. And I have an open loop control signal. So what does the open loop control signal looks like in this particular situation? So I'm going to turn on the thruster 1 for 10 seconds, then turn on the thruster 2 for 10 seconds, then turn on both thruster 1 and thruster 2 for 10 seconds, and so on and so forth. So I have like a time sequence, and I explain what exactly I'm going to do over that time sequence. So that's my open loop control signal. It's not a function of state. I'm not saying that I'll turn on thruster 1 when my height is 200 meters. I'm just saying thruster 1 is going to be on for 10 seconds. So it's not a function of state. This is an open loop control signal. I can define this linearized trajectory z dot t equals to at zt plus bt ut, and at is equal to gradient x and bt So ut is the perturbation to the nominal control signal. So nominal control signal is psi t. I'm going to add this perturbation to the control signal, the nominal control signal, and this would be my linearized state trajectory around the nominal trajectory, and this at is in r n cross n, bt is in r n cross m. I'm just checking if everything looks correct. This is gradient with respect to u times delta u. Awesome, this looks correct. Okay, so this is what the linearized equation around the trajectory is going to look like. Now assume that this is all independent of time. Then in this case, we'll have A independent of time and B is independent of time. Typically speaking, in any system, these are usually time varying, but then we can split the long time horizon into small time horizon, and in those small time horizon, it's not time varying, right? So it's time invariant. So AT doesn't change much and BT doesn't change much. Again, not a good example for rocket, because in rocket everything changes at every point of time. But if you're driving a vehicle and you're doing grocery shopping, when you are driving from grocery store back to your home, or when you're driving from home to the grocery store, A and B are kind of sort of constant. But over a 10-year long horizon, the vehicle undergoes degradation, the battery undergoes degradation, the tires undergo degradation, and so A becomes time varying and B becomes time varying. Every time you brake, your tire wears out. Every time you accelerate, your tire wears out, right? So all of that is changing the state transition function and consequently changing the A and B matrices. But within a specific small time window, these don't really change much. And so you can think of this linearized system as a abstraction of the nominal system around the nominal control action. Okay, so that's pretty much what I have for today. Next class, we are going to start with chapter 2 of the book. So this ends chapter 1 discussion. We are done with chapter 1 of the book. We are done with the appendix of the book. Now we are talking about chapter 2 of the book. Thank you so much, and see you next week on Tuesday.